So far we've talked about specific heat. So specific heat capacity, it's just represented by a C, only works when your substance remains in the same phase. Meaning it doesn't shift from a solid to a liquid or to a gas or anything like that. Latent heat is what's going to be our solution to that. So for our purposes, we're going to have two different types. We will have heat of fusion. Oops, not fusions, fusion. And heat of vaporization. What are we talking about when we say heat of fusion? Well, it is the amount of heat needed to change 1 kilogram of a substance from a solid to a liquid or a liquid to a solid. So I'll put an arrow that goes both directions. It's just the amount of energy that it's going to take to change 1 kilogram of a substance from a solid to a liquid or a liquid to a solid. That's why they call it fusion. So when we go from a solid to a liquid, we're going to be releasing energy. That'll give you a positive one. When we go from a liquid to a solid, liquid to a solid, we're releasing energy, so that'll give you negative. Solid to a liquid, we're gaining energy, so that'll give you a positive. And we represent this with L sub F. That is our latent heat of fusion. Vaporization, same idea. So it's the amount of heat needed to change 1 kilogram of a substance from a liquid to a gas, or a gas to a liquid. We're losing energy when we go from a gas to a liquid, so that'll be negative. If we go from a liquid to a gas, that should be positive. In this case, represented by LV. So the specific heat required, or I should say the specific amount of heat required, is going to be based on both the mass of the substance and the latent heat of a substance. The equation we get for that is Q equals mL. M is going to be the mass in kilograms. This is your latent heat. This is kilograms. This is going to be joules per kilogram. And we have heat over here, which is going to be in joules. I'm going to go ahead and make a graph that shows the latent heat of water as it goes through phase transitions. So I'm going to pause the video. I'll come back. You'll see it on the board. And then when I do that, you can take some time if you need to pause it and draw it for yourself. So what I've done here is I've done a graph of 1 kilogram of ice going from negative 40 degrees Celsius to 120 degrees Celsius. We start down here on our x-axis. This is the heat added from where we started. When I add heat, while it's ice, until I get to the phase change, you notice that my temperature is going to go up, go up, go up until I get to the melting point of ice. When I do that, now you see my temperature doesn't change at all. I'm continuing to add heat, but no temperature change is happening. And when I'm doing that, what that means is all of the energy is going into breaking the molecules apart. This is getting it's a physical change, but all that's happening is the intermolecular forces between the bonds. Energy is going to separating those bonds. So at this point, no temperature change. That's why when you put an ice cube in water, your water is always the exact same temperature, because until your ice completely melts, everything in the mixture is going to be exactly at 0 degrees Celsius. Once we've broken all those intermolecular forces, now the water is going to start to heat up. As we go up, we get to the point where water turns into steam at 100 degrees Celsius. If you've ever noticed that when you put a pot of water on the stove, you can turn it to maximum heat and you don't have to worry about it burning through the bottom of the pot. But if you just leave a pot on the stove empty, it'll burn through it. That's because water is going to keep it at a consistent temperature of 100 degrees Celsius until it all boils away. This is the point where you start to get boiling when you see it in your pot. But notice, this is the biggest section right here. It takes a lot of energy to turn water into steam. That's why water is so good at absorbing heat. Even if you get it up to that maximum temperature, it still takes a bunch of energy to break those intermolecular forces. Then we get all the way over here to steam, and you see at this point that it continues on. Temperature goes up after all of the liquid water has turned into steam. So I want you to notice here two big takeaways. The latent heat of vaporization, for fusion of water is a lot lower than it is for vaporization. And the other thing I want you to remember is anytime you get to these places, all of the heat that you're adding is no longer going into adding kinetic energy. Once you are doing a phase change, that energy is going into breaking intermolecular or overcoming intermolecular forces. Whereas at this point, energy I add is going into kinetic energy. That's why it's getting a higher temperature. They're moving around faster. But anytime I get here, I have to overcome intermolecular forces. So your velocity does not go up. The energy just goes into breaking those bonds. Now I'd like you to use the graph and what we know from here and from the physical constant sheet that is in the resources folder on Schoology under the heat unit. I want you to try and figure out, based on specific heat and on latent heat, the answer to these 5 questions here. And remember, if you're trying to find the area under a graph, length times width usually works. And then for triangles, 1/2 base times height. So I'm going to let you guys pause the video here. This should be A, B, C, D, and E. If it gets cut off on the video, I can't tell. But I want you to go ahead, try and solve for each of these. Pause it now, do your calculations, and when I come back, you'll see what all of the answers are. So let's take a look at the answers here. You'll notice the green ones were ones where there was no phase change. The blue ones are the ones where there is a phase change. And you'll notice that the formulas are different. When there is no phase change, we use our specific heat formula. So Q equals MCAT. For the one where it doesn't, it's ML. This first one is going to be our latent heat of fusion. The second one is going to be our latent heat of vaporization. When we look at the values for C versus L, you'll notice, and you may have messed this up when you were working from your physical constants sheet, you'll notice that on the physical constant sheet, it gives this in terms of kilojoules per kilogram. That's a lot bigger. That's 1,000 times bigger than a regular joule. So you have to make sure when you do this conversion to keep them all in the same unit that you multiply L by 1,000 to get it in terms of joules per kilogram. So you'll notice 2,100, 333,000. 4,186, which this is genuinely one of the highest specific heats of most ordinary substances. 2,260,000. That's a big difference. That's why most of the energy in substances is going to be contained not in them changing temperature, but in the phase transitions that happens between them, the energy that is stored in those intermolecular forces. So when you go through, our first answer is going to be 84,000. We've got a 40-degree temperature change. In this one, we just break it down. I mean, since it's only multiplied by 1 on both of these, it's just going to be whatever your latent heats are. This one, we have a temperature change of 1,000. So we get 418,600. And then down here for the bottom one, we have a temperature change of 20. So we end up with 40,000 and 40,200 joules. Based on what we've just done there, I want you to determine the heat given off as steam cools from 110 degrees Celsius to 0 degrees Celsius and condenses to ice if the sample is 2.3 kilograms. I'll pause the video. It's going to be very similar to what you've just done, and I want you to do the calculations and see if you end up with the same numbers that I have. All right, so for cooling steam and cooling water, both of these are going to be MCATs because it's a specific heat problem. There's no phase change. When it's condensing, that's going to be our vaporization, but because it's in reverse, we have to make it negative. And for freezing to water, we have to make it negative because it's in reverse. So all of these three, or all of those four changes are all going to be releasing energy. That's why we get negative. So when we go down the list, we add them up, we should get that we have almost 7 million joules released. And one last question that I just want you guys to think about is, why does sweating release heat? Take a second, pause, think about it, then we'll come back together and talk. Okay, so basically, let's imagine here's my hand. Very cool hand, Mr. Gillen, very cool. I'm warm, right? Warmer than the air. Particles are going to move around. The highest energy ones are going to have the most energy to go away from me. So what happens is when they go away, now there's lower energy particles left in me. They're going to take energy from my skin. They're going to move it away. And basically all of this happens is while you're moving, you're having some of the highest energy particles that have energy to break those bonds, that have energy to vaporize from liquid. There's only a few of them because you're not near boiling point, but some of them are going to have enough energy that they can break away. And when they do, they've stolen that energy from you, and now you've cooled off some. There's a lot of energy in vaporization, so those particles are stealing a lot of energy away from your body. That's going to be it for latent heat.